So I wanted to do a quick recording just talking about the state of the rendering and some of like the debugging tools or performance troubleshooting profiling tools that I have. So this D2 GPU that runs on the ULX3S FPGA, the HDMI output is streaming here to OBS, and you can see this like approximately 1400 triangles submitted rendering of Apollo from Animal Crossing. This currently runs at like basically 30 FPS, and this is using a diffuse specular pseudo Schlick Fresnel like sort of shading with single nearest texture sampling for like the little zipper and the feet and all this stuff, the eyes and everything. If you look in the sort of the beak here, you can see a little bit of some of the specular and Fresnel stuff on the edges and whatnot. So how do we think about performance? Well, simulations are super, super powerful. So I'll go over what this tool is, but basically the RTL of the actual GPU can run through Verilator, which will produce some C, C++ code that you can then go actually run. So I have a makefile target that effectively does a rendering of the Apollo thing that you just saw. And this lets us run through every single cycle through the mostly the shading pipeline of the GPU to look at what's actually happening and where the stalls are and everything. So with the slider all the way over here, 800 something thousand clock cycles, like this portion of this is done rendering. At the very beginning, nothing's been done. I'll go through how this works in a second, but let me go to like maybe, here. Okay, so what are we looking at? Basically, this is part of like the caller to Apollo. And what you're looking at is a couple different things. So purple here is basically explaining where the rasterizer is. So it's a 2x2 quad that basically moves over the bounding box of a triangle. And when it finds that it's inside all three edge equations, it basically outputs, something is in this quad, might be all four, might be only one, but basically it becomes some work for the shading pipeline to then go do. And then what we have here is basically blue and green. So blue are all of the current contexts. So these are quads that are getting shaded right now somewhere in this system. And we'll look at that in a second. Green is the one that's actively executing on the current cycle right now. So, okay, what's a context? Why do we need it? So every quad that's found to have at least one fragment inside of it obviously needs to get shaded to produce some sort of output. If you were to only run one of those at a time, your performance would be terrible because most operations take more than a clock cycle. So you would do something and you'd have to wait a whole bunch of clock cycles and then do the next thing and do the next thing. And obviously we don't want to do that. And they're all fully pipelined, all of the major functions. So the floating point unit inside the GPU, the integer unit, they're all fully pipelined with initialization interval 1. So every cycle we can introduce a new piece of work into the integer or the floating point pipeline. And so what we do is we have a bunch of contexts, 16, and you can see them numbered 0 to 15 here, and 0, 1, 2, 3, 0, 1, 2, 3. These are the pixels inside of a quad. So every context is like a quad that got shaded. Okay. So the idea is like you submit here, and then on the next cycle, one of the next contexts will run and one of the next contexts. There's a ready list, basically of which contexts are kind of like ready to get scheduled and run on the next cycle. And the scheduler basically just pops out of that list. It's basically just like a FIFO. So if we were to run forward, just to show you this a bit visually, you can kind of see how progress gets made. Okay, and we're at the end of some geometry, so you can see the execution kind of peters out here. But we're in the middle of shading a bunch of geometry. It's fairly well utilized. So you can see there's some into some geometry, and then we get here. So what does a program execution actually look like? So this little dot here is basically the beginning of some shading. So you can see all four within this context number 2 start. That's this green right here. And it takes a number of cycles before they can actually get to their first instruction. On the right-hand side here, you can see what that will be. So there's sort of some shader code. And then where you see this 000102, these are the actual like GPU assembly instructions for the shading pipeline. So the very first thing it does is actually sample the diffuse color. And all of the texture results are palette indices with a special texel 0 in this particular demo, meaning transparent. So basically the first thing it's going to try and do is sample the texture for wherever we are in the triangle. And then if we're at texel palette 0, then it's basically see-through. And so we need to discard it. So that's going to require sampling the texture, load the immediate 1, see if we're less than 1, and then a special discard instruction basically to abort this shader if that happens. Okay, so if you look at it within, this is sort of like one pixel, this one column that I'm in right now, C02 lane 0. So there's some setup, and then there's a texture sample. And then basically these little red hash marks mean it's not eligible yet. So the actual result of this operation is not ready yet. And this is all cycle accurate. It's all based on the actual like hardware description RTL. At this point, the result of the texture sample is actually ready, but we're not scheduled to run it yet. So it's like a less, it's a more muted color. Then at this point, we run that move I instruction, which moves the immediate 1 into the R1 register. That takes some time as well. And we're ready again. A couple cycles later, we get to run again to do the sign less than operation. And there's this control flow operation to do maybe a discard. Okay. So none of these will discard because it's not on the fringe or whatever for this particular model. So they'll keep executing. And now we have some floating point math, and you can kind of like, I'm just going to hold down. You can see how we make some progress through here. You also notice that this assembly instruction 12 is actually related to an earlier, quite a bit earlier shading instruction. So the compiler does a little bit of stuff about trying to hide latency. So it will try and reorder like integer and floating point operations so long as it doesn't violate like the semantics of the program, so that it can get hide loads and do a couple of other clever things, but it's not very effective yet. Okay, so basically you can, and this little blue arrow is just showing like what the dependency is. It's always kind of trivial, but it looks nice. So you can see, okay, so what's interesting? You can see here on the right-hand side, these are the active functional units. So there is basically at this moment in time, almost always some floating point operation getting issued. Much less often is some sort of integer instruction. And then periodically we also have some unpack operations. These are the ones that go from like floating point color to packed RGB 565 or other formats that the frame buffer actually uses. So you can kind of see how the functional units are utilized. And then let's see, this is frame buffer write back. So this is an immediate mode render. The frame buffer has like a cache on the GPU, basically like you're always operating on like lines of pixels, and if that line of the pixels in the cache, then you just operate directly out of the cache. If it doesn't have that, there's some configuration to see whether or not you need to pull it from the frame buffer first, and then afterwards, obviously you need to write it back when things are done. Let's see what else to point out here. So this is an interesting observation as well. Currently the GPU is single issue, so we've got like the potential to, if you look right here, for instance, we actually could in this particular cycle issue floating point operations here. And ideally we would also issue an integer operation, right? In this cycle, we're not actually using the integer pipeline at all, just the float. And it's the same for all of them. All of these only ever issue to a single pipeline in one cycle. If we could get dual issue to work, which I'm kind of looking into, then this particular area would be much, much faster, right? Because we'd be able to issue an integer and a float at the same time, so long as there's something ready to do on both. And that would be a pretty big win for this particular case. It's highly dependent on the shader, mix of floating point and integer. Once we support dual issue, it's also possible to think about things like multiple floating point issues. Like you could imagine I have two FPUs, and then we could go through a floating point twice as fast. But there's a lot of issues with the register file and everything. Anyway, it's kind of cool to see just visually how as the cycles go on, basically it's sort of round robining here over different quads to make progress. And that's like the typical pattern here. Yeah, I think that's mostly it. I just wanted to kind of give an overview of this little tool, and it's been pretty useful to sort of see like how the utilization is and understand performance.